All right. Hello. Good morning. Sorry for the late start this morning. I'm just trying to get everything ready here. So behind me, of course, this is the notes from before. Um, let's see. I also have Mastering Chemistry open. We're going to look at Blackboard again today. Today is really focused on answering your questions and getting ready for the upcoming exam this week. So good morning, Daisy. Good morning, Jennifer. It is Election Day. So if you haven't had a chance to vote, please go out and do so. Remember that Illinois allows you to register on Election Day, so you don't have to have prepared anything or be registered in the past. You can just go to your local polling place and vote if you haven't gotten a chance to. Keep your distance and wear a mask, but otherwise, it should be relatively safe. The um, the second exam is going to be similar to the first, with a couple changes that I've noted on Blackboard, but it will this time we're not going to use mastering chemistry. That just caused too many headaches between honor lock and trying to get everything set up there. So it's not going to be inside mastering chemistry. It's going to be inside Blackboard. It'll be a similar format test, primarily multiple choice with some fill in the blank answers as well. There's also some. There will also be some question where you have to draw and then upload your answer. So just like when you turn in your homework, you'll have to do that. The timing and the size of it and everything should be, and the types of questions should be pretty similar to what you saw in the last exam. I'm also going to give the option of the live one-on-one exam. I'm still trying to set up time slots for that, but it'll likely be next weekend is what I'm looking at. This coming weekend for those time slots. Um, Good question. Will I do a practice test as well? So yes. I don't have the problem is I don't have anything inside of Blackboard to do as a practice test. I can give you the written tests, which I believe are on Blackboard, from last or from years past, but they weren't in a digital format and they were um a little bit different with material. I can definitely do a small practice test on Blackboard just so you see what it's gonna look like, but you've done Blackboard quizzes like the pre-labs and things were set up as quizzes, so it'll be similar to that. But yeah, I'll try to get more information out there for you. The other thing that's a little bit different that you can see on Blackboard is rather than everything being due Sunday night, it's due Monday around dinner time. And the reason for that is last exam, I went to bed at my normal bedtime, and which was before the exam was due. And so some people who were starting the exam really late um, didn't have the opportunity really for me to answer their questions because it was too late at night. So rather than doing Sunday at midnight, we're going to do Monday at dinner time. So that way you can still work on it all Sunday if you want. But if you are trying to get it done at the last minute, at least that's like during the daytime when I'll be around to answer your questions. Um, so that's the exam coming up. The other thing you'll notice on Blackboard is there's basically nothing else due this week. So there will be a lab tomorrow. Hopefully, if everything goes okay. I know we all haven't seen each other for a while, so we should be good to go back to campus. But there's always the chance that someone else who was in that room tests positive and we get canceled. So we will hopefully be there tomorrow for group B01, and there is a pre-lab as usual for that lab. It's just a paper one. You can do it on paper and bring it, or you can um, submit it online. There is no mastering chemistry this week. There's no post lab due this week. So even if you do the lab tomorrow, your lab report is not actually due until the following week. There's no virtual lab this week, but again, that will be next week, kind of for everybody. And then you'll have the week of Thanksgiving to finish that if you want also, since we don't really have a lot to do that week. So just some scheduling changes. I just want to make this week pretty easy so that you can really focus on the exam. Because of the way the schedule is, we are going to talk a little bit about acids and bases. It's not on the exam, but if you want to use this time more for exam review, that's great, and we can always do an extra. I can do an extra time somewhere, that maybe you don't even want to listen to until after the exam about acids and bases. Yes, sorry, BO3 is tomorrow. Yes. Section BO3 should be coming to lab tomorrow. Okay, so there was another question. Is there a time limit? Yes, the exam will have a time limit. It will be similar to the last one. I don't remember exactly. There's a few more questions on this one, so it may be a little bit longer, but right around the same amount of time. Okay, other questions about the exam or schedule or any of that kind of stuff coming up this week? All right. So then I want to look at, before we go into specific questions. Oh, that's the chat. I didn't want that there. Oh, thank you. Let me check Discord here. Oh, okay. Yeah, Monica's saying having trouble signing into to YouTube. So send your questions here. Yes, I will keep that open. Go ahead and send your questions. All right, so I got to change my browser here so I can get to the Blackboard. All right, so here's Blackboard. Okay, so just to remind you, for this exam, we're going to start with week 7. So these are your goals for weeks from chemical reactions and energy. Then week 8, unit conversions in moles. Week 9, gases and intermolecular forces. And then last week, solutions and mixtures. So those will be the things to focus on for the exam. But as we've said before, it's really a cumulative exam. And it doesn't mean that I'm going to go back into week 2 and ask you some very, random question from some specific thing about one of those. But many of these are required for the later things. So for example, we've drawn a lot of Lewis structures when we talk about intermolecular forces, because we have to know the Lewis structures to know how the polarity is going to work out in a molecule. We have to know how to name compounds in order to write chemical equations of those compounds. So even though we're not in week 4, you still have to be able to do compound naming. So really, all of these skills are cumulative. The exam is cumulative, but we're going to focus on these most recent skills. So, what kinds of things do you want to go over now? Where are you having the most trouble? I also have the Mastering Chemistry open, so if you have questions about those, we can get into those. What do you think? Conversions, great. Yeah, that's a good place to start. Let's do that. Is there a specific part of conversions that's giving you the most trouble, or just kind of go over how to do it again in general? Like, are there types of questions that you seem to get wrong a lot? Let's pull up our notes from that. Yeah, knowing where to start. That's good because that is always a trouble, right? So let's find some of these questions that we didn't do, or maybe some of the ones that we did do, and just so we have some numbers here. Do you have to memorize formulas for exams? No, but it kind of depends on what you mean by formulas. So you do need to know the things that are listed that you need to know. So like you need to know your metric prefixes, how to do those conversions. You do not need to memorize temperature formulas; those would be given to you. You do not need to memorize conversions between systems. So how to convert between like miles and kilometers or pounds and kilograms, things like those would always be given to you. You should know things like how to calculate density, how to calculate mass percent concentration and molarity, some of those types of things that we've done a lot. I don't know if that's really memorizing a formula so much as just knowing the definition of what those units mean. Let's take a look at one of these with density because that's something that often is a little bit confusing. I can't keep looking for the one that I'm looking at. All right. Let's take a look at this one. We already did it, but we'll take a look again. Number 26. A piece of gold weighs this much grams and is placed into 41.1 milliliters of acetone in a graduated cylinder. The gold sinks to the bottom and raises the level of acetone to 66.9 milliliters. And so the question then is, I mean, the main question of this part then is, what is the density of the gold? So to get that, we have to first know the definition of density. We have to know that density is mass divided by volume. And generally there would be a specific unit given here. So like report the density in grams per milliliter or grams per cubic centimeter. If there's not, you can use whatever units you want. So in order to calculate the density, we need two numbers. We need mass and we need volume. We need those to be related, that is, of the same thing. So we have the mass of the gold, that's just given here. And then we have two volumes of acetone. And one of the issues with questions like this is somebody might say, well, which number do I use? Do I use the 41.1 and the 66.9 or the 66.9? And that's not really the right way of going about these questions. Don't just look at the numbers and kind of say, oh, which one do I pick to put in the formula? You need to use more of your brain than that. You need to read the question and try to understand what's happening, physically what's happening, and then what's being asked. So in this case, the gold is placed into this much acetone. So does it make sense that we would use the total volume of acetone as the volume of gold? No. And one way that can also help you with that is just being more specific with your units. So yes, this is our formula for density. Oops. But maybe maybe it makes more sense. Well, I lost my V. I don't know why that happened. It might be more helpful if you use words when you're describing your units. So maybe a better way to look at this is to say the density of gold is the mass of the gold over volume of gold. So when we write that all out, now it becomes more obvious that if this is a volume of acetone and this is another volume of acetone, that neither of those are going to be the volume of the gold. If we just have V, because all we remembered was D equals M over V, then maybe it's confusing about which volume is the volume. But if we write it all out and we understand that the density of the gold is the mass of the gold divided by the volume of the gold, then it makes a little bit more sense what we're supposed to use and what we're not. So then we read the question and we think about physically what's happening. A piece of gold is placed into the acetone, the gold sinks to the bottom, and the acetone level rises up. And so then we can know that that rise is due to the gold being placed in the cylinder. That's what caused it to rise. So going from this to this, that means that the actual volume of gold is the difference between those, and that's what we calculated here. So the volume of gold is this, and then we can do our density calculation. All right. So one thing when we think about unit conversions, when we talk about where to start or what to do, think about it physically. What is being described? What is happening? What is it that is what is it that we want and what is it that we are given? So let's look at another one here. We already did this one, number 28, but again, let's just erase everything and restart here how we would do a conversion like this. All right. A backpacker carries 2.5 liters of white gas as fuel for the stove. How many kilograms does the fuel add to her load? White fuel density is 0.79 grams per centimeter cubed. Show your work, don't forget units. Okay. So again, before we start with numbers or anything, let's think about physically what's happening. We've got a bottle, 2.5 liters, it's a lot, of gas. And what is it that we want to know? How many kilograms does that add? I see another question from Monica. Yeah, we'll get it. We'll jump over to H10 exercises after this. So we're talking about this 2.5 liters of white gas, and then we want to know the weight. So this tells us, and then there's another number given here. So let's talk about the possible confusion there. White fuel density is 0.79 grams per cubic centimeter. So this is the density of the fuel. So do we start with our conversion with liters, or do we start with grams per centimeter cubed? Well, the best clue there, I think, is focusing on the question. What is it that you want to ultimately solve for? The question says, how many kilograms does the fuel add to her load? So ultimately, we want an answer in kilograms. So, so we want to know, like, how much does this much liquid, this volume of liquid, weigh? So what we have to do is take liters that we're given, and we have to turn it into kilograms. So we have to find the mass of a given volume. And whenever we want to relate mass and volume, we need density. But notice the density is a this per this kind of unit, like grams per cubic centimeter. And we've seen several of those. There's molarity, right, is a moles per liter. There's various things like that. But our answer, we don't want a something per something unit. We want just kilograms. So that tells us we're probably not going to start with the density. We're going to start with the quantity that we're given of the actual gas. So we want to know, how do we turn liters into kilograms? And this would be great if we had a density that was kilograms per liter, but we don't. We have a density that's grams per cubic centimeter. So this is going to work best if we can get volume in cubic centimeters or milliliters, which we know are equivalent, and then convert that to grams. So once we have milliliters, we can get grams by using the density, because the density interrelates those two quantities. And then what the other parts of the conversion then are converting liters to milliliters and then grams to kilograms. So liters to milliliters, that's a metric conversion we can do. Milliliters to grams, we use the density, and then grams to kilograms is another metric conversion. So Monica asks, most of the time it doesn't make sense to understand what is physically happening. Just try to figure out what to do, where to put the numbers in memorized formulas. Um, yeah, I think following the units through in a conversion can be one way of doing that more algorithmically or programmatically, if that works better for you, to say, okay, I'm starting with this unit, and then I'm going to turn it into this, and I'm going to turn it into this, and I'm going to turn it into this by canceling. You can do it that way if whatever's happening doesn't really make sense to you. The problem with putting numbers in memorized formulas is that doesn't necessarily make sense. So like if you know that the density formula is D equals M over V, that's fine if the question just says, here's the mass, here's the volume, solve for the density. Then great, you just plug it in. Or if the problem says, here's the density, here's the volume, solve for the mass. So anytime, then you just put them in the equation. The problem comes when anything else is asked to use those quantities, like in number 28 here. So here we have a density, and we need to use that more like a conversion factor rather than just a formula. So unit conversions don't really follow that idea of plugging numbers into a formula. They're more about turning one unit into another in sequence. And if it's confusing to have that big string of units, as we do sometimes with this, it's also fine to just do it one step at a time. So to say, okay, I came up with this plan here that I want ultimately liters to become kilograms, and I know I'm going to do that. I'll finish this. I know I'm going to do that by first converting to milliliters, and then converting to grams, and then converting to kilograms. But rather than do it all in one big string like we did last time, let's do it more kind of step by step and see what's going on here. So what this plan tells us is that overall we want liters to kilograms, but in order to get that, we have to go first to milliliters, then to grams, and then to kilograms. So let's do that step by step. We want to know how many milliliters are 2.5 liters. So 2.5 liters times, and we want a unit that cancels liters and instead gives us milliliters. Notice again that I put the units down first and then the numbers. So I'm not thinking, oh, I have to multiply this by 1,000. I'm thinking I have to cancel liters and instead have milliliters. Because if I were doing the opposite, I would just put the 1,000 on the bottom instead of the top if I were going from milliliters to liters. All right, so 2.5 liters times 1,000 milliliters is 2,500 milliliters. Okay, so that's step one. Next step is to go from milliliters to grams. So 2,500 milliliters. And I want to cancel milliliters and instead have grams. And now I want to know how many grams are in a milliliter. Now that's not just a standard conversion because that's a density. And every substance is going to have a little bit different density. So in this case, this fuel that I'm talking about in this problem, the density is 0.79 grams per milliliter or per cubic centimeter. We know those are the same. So that's how we find the relationship between mass and volume for this particular fuel. All right, so we can do that. 2,500 times 0.79 is 1975, and that's now grams. I'm not worried about significant figures right now. We're just going to do the calculations. Okay, so I went liters to milliliters. I went milliliters to grams using the density. And now my final step is to go from grams to kilograms because the question asks for the answer in kilograms. So for that last step, we're going to take 1,975 grams and we're going to cancel grams and then still have kilograms. 1,000 grams per kilogram. 1.975 kilograms. And then we can kind of round that, however. Remember that the convention is generally to use about the same number of significant figures as the problem, but that's not something that you're going to be graded on. So in this case, if we had two significant figures, we would call this 2.0 kilograms. If we wanted to report it to three significant figures, we would call it 1.98 kilograms. All right. Questions about that one? Um, Mostly, I mean, what do you mean by typical? I guess is the question. Like all of these are typical metric units, I would say. Where is that list? It's up here. These are the ones that you should know. I guess some are more common than others. Like definitely ones that we've seen more than others would be like kilo, centi, milli. Um, yeah, I think if you remember them in order is a good way to do it. Deca and deci are kind of like on either side of 10 to the 1, 10 to the minus 1. I I don't think I would use hecto. I haven't seen that very often. I'm trying to remember. There's pretty much no way that's on the exam, but definitely kilo, mega, giga. If you just remember that those are 10 to the third or 1,000 away from each other, and then milli, micro, nano, same idea, 1,000 away from each other on the smaller side. Um, one tip that somebody, I don't know if they want to take credit for it or not, so I'll just say somebody had that can be useful if you're having an exam where you don't have notes, but you're concerned that you don't have all the stuff really truly deeply memorized as well as you can. One thing you can do, since you are allowed to write on scratch paper, is before you start the exam, try to like get all as much as you can in your short-term memory by just looking at it, and then once the exam starts, you can write it down on your blank scratch paper. So that can be a way, like if there's a few things that you just cannot seem to remember, that's a good way to make sure that they're there for you. Or like the names of the intermolecular forces or something like that. You can't get too much because there's not enough room in your short-term memory for too much. But if there's a couple things that you just can't seem to get in your brain to stay there in your brain, that can be a good way of still having that stuff on the exam by just writing it on your scrap paper as once the exam starts. All right. The other thing I'll say about unit conversions that will help you on the exam, I think, is again to think about what's going on. So let's go back to that problem that we just did. Okay. You've got 2.5 liters of gas, right? Like about this much. You know about how much 2.5 liters is, right? It's like, you think about like a 2 liter of soda or something, and it's like a little bit bigger than that. These problems are always going to kind of make sense. Like there's I'm not going to just make up some ridiculous substance that doesn't make sense. So you can think about, all right, like physically, what's reasonable for that much for that much gas to weigh? Again, it depends on the density, but we know that water's density is 1 gram per cubic centimeter. So if you have basically a 2-liter bottle or a little bit bigger than that filled with water, think about how much that weighs or how that would feel in your hands. And then think about, okay, well, instead it's filled with this gas that's a little bit lighter than water, a little bit lighter than water. So you would expect this to be a little bit lighter than the same bottle about this big filled with water. And the reason we go through all of this is, let's say you flipped one of these conversions or something, right? Like this bottom one. Let's say you accidentally flipped that one over, and so you ended up multiplying by 1,000 instead of dividing by 1,000. Well, then you would get an answer that the fuel in the stove weighs about 2 million kilograms, right? Because that's what you would get if you multiplied this number by 1,000. So if you happen to flip this, you would get an answer of about 2 million kilograms. And so if you're thinking about that realistically, you have a bottle of a substance a little bit lighter than water that's about this big. Is that going to weigh 2 million kilograms? No. So that's a good clue that something is wrong there and you need to go back. And if it's something big like that, chances are it's because you flipped a unit somewhere. So you can go back through and check your units and make sure everything's canceling appropriately, and so on. Same thing over here. Let's say you, at the beginning of the problem, you accidentally flipped this one and you divided by 1,000 instead of multiplied by 1,000. Well, then you would have gotten an answer like 0.002 kilograms, so essentially 2 grams. So would this much liquid weigh 2 grams? No, right? That's 2 grams is like a small amount that's hard to measure on the balances in lab sometimes. So that also doesn't make sense. So always think about with these conversions, does my answer make sense for the thing I'm trying to measure? If you're doing mole conversions with Avogadro's number, the only thing that really makes sense for that many things is if you're talking about a number of atoms or a number of molecules or something like that. So if you get you get a question that asks how many grams are in something, and you get like something times 10 to the 23 grams, chances are something got messed up in there because that would be a ridiculous number of grams. So you can think about those kinds of things. Does this answer actually make sense as you do it? All right, let's jump over to this one to answer Monica's question about I think you're talking about the concentrations there. So stuff like this. Go back up to the question. Detailed explanation about solving exercises as we had on H10. So there were basically 2 types of questions here in H10. One was actually calculating concentration. So that's what we did first. And those are questions like, what would the concentration be, either in mass percent or molarity, when given the quantities of solute and solution? Yeah, we'll do 31 also. So just like these are the straightforward like plugging numbers into an equation. You know the definition of mass percent, you know the definition of molarity, and so you're given the solute, you're given the total solution amount, and you calculate. We knew that this one was a weird one, but we calculate the concentration from that. Then after that, we did these dilution calculations. To get the molarity, we'll be given the molar mass of the compound. Well, you'll be given a periodic table, so you can calculate it from there. I have to look back at the question. Sometimes I included the molar mass also just to make it quicker. But you can always calculate it from the periodic table if it's not given. All right, let's take a look at 31. The molarity of a solution with 9 grams of potassium carbonate in enough water to make 67 milliliters of solution is. So this is that type of a question that we just talked about. And how do we know that? Well, first, we know that the question, even though it's worded a little bit weird, the question is asking what is the molarity of this solution? And we know that molarity is moles of solute divided by liters of solution. So we have moles of solute, kind of. We have grams of solute, but we can get that into moles. And then we have liters of solution, kind of. We have milliliters of solution. So we want to make that into moles. We got to figure out how to get that into moles, and then we got to figure out how to get that 67 milliliters into liters, so we can have moles of solute divided by liters of solution. So let's do this. All right, 9 grams of potassium carbonate. We're going to convert from grams to moles. So to do that, we need the molar mass. So that would be great if it were given, but it's not, so we have to find it from the periodic table. So let's look it up here. So we got 2 potassiums, 1 carbon, 3 oxygens. We add all that up and we get 138. Thank you. Yes. Okay, so that means 9 divided by 138 is 0.0652 moles. And really, I mean, we could only use one significant figure because of the question, but let's use a couple just so we know what we're doing. So that's how many moles of potassium carbonate we have, and that's our solute, and that's going to end up being our numerator in our molarity expression. So that's going to go up there. Okay. Next part then is we need to figure out how many liters this is. So maybe by now you've gotten quick at going between liters and milliliters. Depending on where you grew up, that might be kind of second nature to you. But it is a difference of 1,000, so we can set up another conversion, divide this by 1,000, and that's 0.067 liters. Right, 67 divided by 1,000 is 0.067. So now we have both parts of our expression. We have moles of solute, 0.0652, and we have liters of solution, 0.067 liters of solution. So we divide those two. And I get 0.973, and so we say 0.973 molar. That's the molarity of the solution. Because we're, what does it say to report to? 2 significant figures. So we would call that 0.97 molar. All right, take a look at, compare this one, number 31, to number 32. In number 32, we still are asking for, or being asked for, what is the molarity? But this time we're being given moles instead of grams. And once again, we're given milliliters. So this is actually a little bit quicker of a question because we don't have to do that conversion, that first conversion using the molar mass. We're already given the amount of solute in moles. So this one we can just say 10 moles divided by 0.135 liters, we do have to convert that to liters, is the molarity of the resulting solution. Okay, now let's compare that to another question that sounds similar but uses a little bit different technique to solve, and that's this one, number 33. So in 33, what is the final molarity of a solution prepared by diluting 5 milliliters of 6 molar HCl to 60 milliliters? So notice the question part of this one is very similar. What is the molarity? But in this case, we can't just use our molarity definition because we're not given moles of solute. We're not given liters of solution. We're given a volume of a different molarity solution and then a volume that we ultimately want. And whenever you see a question of this type, and you'll notice like there's one there, anytime it says generally diluting or adding water, that's when we can use our dilution equation. Now I should say also, you can do this the same way. We can calculate how many moles are involved here and then calculate a new molarity. That's really how the dilution equation works anyway. But if we recognize that word, we can save ourselves a little bit of trouble by recognizing what's happening here. And again, it helps to think about this physically. We have a small amount of a concentrated solution. We're adding water to it to make it less concentrated. And this is that initial concentration times initial volume equals final concentration times final volume. So this is our initial volume, this is our initial concentration, and this is our final volume. So we just need to solve for the final concentration using the dilution equation from up here. So finding that word diluting then you can just use the dilution formula. I think the only thing to watch out for there is not to mix those two things up. If you're making a solution from solute and solvent, you're mixing them together that way, then we're talking about the definition. We're talking about how much solute and how much solution. If you're starting with an already existing solution and then just adding water to dilute it, that's when we can use the dilution equation. In my experience, the trouble there, hang on, let me calculate it and check you there before I go on. So we're going to go 5 times 60 divided by 60 is 5 times 6 divided by 60. Sorry, 5 milliliters times 6 molar divided by 60 milliliters should, yes, be 0.5. Says two significant figures, so we'll say 0.50 molar. Okay. Oh, so I was saying where I've seen problems with this in the past, the dilution equation is pretty easy to remember and fairly easy to use once you get used to it. So I have issues, or I generally see issues with people trying to use the dilution equation when it is not appropriate. So like, you have something like up here, and somebody tries to fit that dilution equation into there, and that's when it causes problems because it doesn't work. You have to you have to think about, again, physically what's going on. Are you adding water to a more concentrated solution to make it less concentrated? That's dilution. Are you taking a solute and then dissolving it and making a solution? That's not dilution. That's making a solution. So that's a little bit different. All right. What else do you want to talk about? Yes, still know the polyatomic and monoatomic ions. You just need to know the ones from the list. It's on Blackboard from that chapter. It says, know these particular ones. So yes, you should know those. So think about, for example, this question we did up here to calculate the molarity. This question was nice in that it gave you the formula of potassium carbonate, but you should be able to still do this question if you're only given the name potassium carbonate, and you need to find that formula. And notice that if you didn't do this right, and if you said that potassium carbonate was, let's say, KCO3 or KCO4 or K3CO4, or some wrong formula, then you would also likely get the molar mass wrong, and so then the whole thing would end up being wrong. So yes, definitely go back and review the naming and writing down compounds from names if you haven't thought about that in a while. Sorry, I mean it's Halloween, so you know it's gonna be a little scary around this time of year. Next year I'll dress up as naming compounds somehow. Yeah, let's talk more about intermolecular forces. Um, oh, that was the last one, right? It came up in solutions as well. Okay, so quick review of the types of forces and then how we ask about those or how we think about those. Sorry, got up into gases along again. All right, so first, in the London dispersion forces or just dispersion forces. Um, these are most important when you have nonpolar molecules, but they are present in all molecules. So any molecule that has anything that has electrons, which is going to be any molecule, is going to potentially have dispersion forces. And the strength of those forces is determined by the mass and the shape. And we should say also there's this other part that is related to the atomic mass that we learned about later called the polarizability. You don't necessarily need to know the details of that, but just the idea that the more electrons there are and the more that they're spread out, the bigger the cloud is, the more they can be pushed around to make this thing happen that we saw up here. The more they can have a negative and a positive side, and the more they can be subject to that induction. So big, floppy electron clouds are more polarizable, and that's why we say that um, bigger atoms and bigger molecules have stronger dispersion forces. Right? So it's not really the atomic mass because the nucleus doesn't have anything to do with it, but it is the amount of electrons. And so atomic mass is a good proxy for that. So generally, if things are totally nonpolar, big molecules are going to have stronger forces than small molecules. But there are three different types primarily of forces that we talked about. So there's also these dipole forces when you have polar molecules, and those are a little bit stronger than dispersion forces. So if you have molecules of the same size or similar size, then you would expect that a molecule that can have polar parts will have stronger forces than a molecule that is purely nonpolar. Notice I said if they're similar size. If you're trying to compare molecules that have different forces and different sizes, that's really difficult. So for example, water. We know water has really special properties, has a high boiling point, strong hydrogen bonding intermolecular forces, and its molecular weight is 18. So comparing that against other small molecules, we expect water to always have the smaller or the stronger forces, which it does. But if we're comparing water against, say some big hydrocarbon molecules like octane and gasoline, well, now it becomes a little more even. Actually, octane's boiling point is a little bit higher than water. So even though octane has those dispersion forces, because it's so much bigger, those kind of end up overtaking water. Think about things like waxes. You can have solids that are totally held together by nonpolar forces, but they're just so big that it ends up those forces end up adding up. So if you're comparing similar sized molecules, you want to look primarily at the types of forces. If you're comparing different sized molecules, hopefully you would only have to compare them if they have the same types of forces. And then the strongest types of intermolecular forces are the hydrogen bonding for neutral molecules and ion dipole, so if you have ions in solution. Yeah, let's look at mastering chemistry from solutions number 37. Okay, this is the one about dialysis. I'm almost got it. Okay, here it is. So this one will actually make, I think, more sense after we do lab these next couple weeks. If you, which I know not everybody's going to do lab this week, but if you read through the lab this week and kind of see what's happening, that may be helpful for this idea. But basically, we're actually physically going to do this exact thing. We're going to put some stuff in a dialysis bag and then immerse it in distilled water. So let's draw a picture of what that would look like. So um, here's a beaker. And there is some distilled or deionized water in here. So just pure water in there. Then into that, we put a dialysis bag. A dialysis bag is a semi-permeable membrane that we're going to fill with liquid and kind of tie it off. It's actually more like a tube than a bag, but we're going to tie it off at both ends so it becomes like a bag. And inside that dialysis bag, inside the dialysis bag, we're going to put some ions like chloride and sodium. We're going to put some sugar, some glucose, and we're going to put some starch. And then in the question, in that particular mastering chemistry question, it also talked about albumin. So the important thing to know here is a semi-permeable membrane, which this dialysis bag is, or tubing. Sometimes it's called dialysis tubing. This semi-permeable membrane can pass small molecules, but it cannot pass colloidal particles or suspended particles. So a semi-permeable membrane only passes molecules in solution and water. It can also pass water. So the water is going back and forth through here, and then particles in solution are going back and forth through here. So that would be chloride, sodium, and sugar can all get out of the bag. So an equilibrium is going to be set up where the water is going back and forth, and then actually, because of osmosis, more water is going to be going into the bag. But also, the particles that are in solution, the chloride, the sodium, and the sugar, can pass out of the bag. But larger colloidal particles, like starches and proteins, cannot make it out of the bag. So they're stuck inside the bag. So after some time, we would expect, and this is what we're going to see in lab, we would expect that the chloride, the sodium, the sugar all end up and are detectable outside in this DI water. But starch, proteins, and suspension particles are going to be stuck in the bag and can't make it out because those molecules are just too big. So they can't pass through this semi-permeable membrane through this procedure known as dialysis. So if we go back to this question then, we've got the sodium chloride will be found outside the bag, but the other two will not because they're too large. They're colloidal particles. And then which substances will be inside the bag? Well, all of them should stay inside the bag, right? Because they started inside the bag, and yes, the salt particles will come out, but they won't all come out. It'll keep moving until the concentration is roughly equal. So water and salt and sodium and chloride ions will move through the membrane back and forth until they equalize. They're not just going to leave the bag. All right, and then the same thing down here, the dialyzing, same idea. How do we get the most salt out of the water? Well, if we want to get the most salt out of the water, we've got to replace the water with fresh distilled water periodically, because as soon as that concentrations equalize, there's not going to be any more particles coming out of the bag. But if you dump that water out and then put fresh deionized water there, then more particles can come out. And so that's how dialysis, like human dialysis or artificial outside the body dialysis works, is that a special solution that is missing or that is low concentration in the things that you want to remove is constantly cycled out. The blood is constantly put in contact with that through a dialysis membrane, and so those particles can continue to come out. All right, we got about 5 more minutes. Let's look at the next one also. All right, so the same idea here. We've got a figure that shows a semi-permeable membrane with pure water on one side and some sodium chloride on the other. And then it's talking about the water moving back and forth. And eventually, over time, the water actually goes into the right side and ends up sort of pushing that up. So which one will decrease in volume? Well, the one that is lower in concentration will decrease in volume, because the water will move toward where there's more concentration. The reason it's important that they say starch here is a solute is because then it takes away that issue of the ions also. So if, a lot of times this example is with like sodium chloride, the sodium chloride is also moving. Yeah, good question. How does this relate to osmotic pressure? Well, imagine we're doing this. In order for this liquid to actually push upward, it has to push against the atmosphere. So that's actually creating a pressure. In order to push water up something, you're pushing up against the atmosphere. So this is really, the solution is doing work here. So the water that is moving in this diagram from left to right is actually exerting a pressure on that membrane, and then a pressure against the atmosphere as well. Is there a pressure here? No, this is just sorting them. So osmosis, when water is moving, is creating a pressure, and that's often referred to as the osmotic pressure. Is there a question about that one next also? Can't remember if this one talks about that or not. No, this is the blood cell one. But let's take a look at this one, because this is a little bit different from what you might find on the well, no, I guess not. Let's take a look at this one. So in this case, a blood cell undergoing crenation, lysis, or no change. What are those solutions, and how would you know that? So first, reviewing those definitions, crenation is when the higher concentration is outside the cell, so that all the water from inside the cell moves out and the cell shrivels up. Lysis is when the higher concentration is inside the cell, so the water moves into the cell and causes it to burst. And then no change is when it's isotonic. So that's another way to think about osmotic pressure, is the pressure that's being exerted on the cell walls of the blood cell. So in this case, we would expect lysis with distilled water, because if there's no ions in the water, then all of that water is going to go into the blood cell to try to equalize the concentration, and it's going to make it burst. For these others, we need to know some more information. So we need to know what is normal concentration? What is isotonic concentration? And the two isotonic concentrations you should know are 0.9% sodium chloride is isotonic, and 5% glucose is isotonic. So 5% glucose should have no change because that's isotonic to the cell. That's the same osmotic pressure as the cell. But these two are going to be both much higher concentrations than what the cell than what's inside the cell. And so in both of those cases, the water is going to come out of the cell and cause it to crenate, to shrivel up. So notice common isotonic solutions, IV solutions, include 0.9% sodium chloride and 5% glucose. So don't mix those up. The reason the concentration is so much lower is because of something we didn't really talk about called equivalence. So it has to do with the osmotic pressure is determined by the number of particles in solution. For every mole of sodium chloride, you actually split up into sodium ions and chloride ions. So that's kind of double the concentration of total particles, and then also the molar masses come into that as well. Glucose doesn't split up in solution, so however many moles of glucose this is, that's how many particles are in solution. We did talk about this. Oops, wrong one. I think it was in the 10th handout. Let me see. Yeah, when we looked at all these things. Yeah, and then we talked down here. So the normal concentration or the isotonic concentration of glucose in blood cells is 5%. Saline sodium chloride would be 0.9%. All right. All right. I've got to get going this morning, but we will come back and do more of this on Thursday evening. And we can still just talk about the exam. I want to make sure you have your questions answered. That's more of a priority than moving on to new stuff. So plan on coming back with more questions, more stuff to talk about. The only thing I would ask is if you really want to just get the exam out of the way and you plan to do it as soon as it opens up tomorrow, please don't come tell us about it, because, you know. Oh, I will also get some signups up, so for those of you who want to sign up for live exams this weekend. Okay, as always, you can send me questions on email or Discord. You can set up appointments with me to meet you online, but privately at other times. Or if you have a study group or something that you want to meet, we can do that as well. Hopefully, sorry to add to all your extra stress this week with the exam, but I think it'll be okay, and we'll try to get you as prepared as possible. So I'll see half of you tomorrow at lab, and the rest of you online. So thanks, everybody. Have a good day. Go vote if you haven't already, if you can.